Hello everybody, this is Mika Seppälä. In this video I take a closer look to improper integrals. I will discuss a comparison theorem that allows us to decide whether an improper integral converges or diverges by comparing that to simpler, similar improper integrals. An integral from a to b f of x dx is improper if either the interval of integration is infinitely long, that is, if a equals negative infinity or b the positive infinity or both, or if the function f is either discontinuous or undefined at some points of the interval of integration, or maybe all these things happen at the same time. Such integrals cannot be defined by Riemann sums. Different methods must be used to define those integrals. As an example of that, let us now assume that the function f is continuous on the interval from a to b. This is half open, a is included, b not. B may be the infinity. Now, if the limit as beta goes towards b through numbers less than b of integrals from a to beta fx dx, if this limit exists and is finite, we say that the improper integral from a to b f of x dx converges and that its value is this limit. If the integral from a to b f of x dx does not converge, then we say that it diverges. The integral from 1 to the infinity dx divided by x to the power p is improper because the interval of integration is infinitely long. The function to be integrated is continuous on this interval. Therefore, the integral from 1 to the infinity dx divided by x to the power p is limit as b goes to the infinity of integrals over the interval from 1 to b. Now let us assume that p is different from 1. If p equals 1, then we have to integrate dx divided by x. An antiderivative of that is a natural logarithm of the absolute value of x. Now p is assumed to be different from 1. Let us write dx divided by x to the power p as x to the power negative of p dx. It is easy to integrate this function over the interval from 1 to b. An antiderivative of x to the power negative of p is x to the power negative of p plus 1 divided by negative p plus 1. Therefore, the integral from 1 to b, x to the power negative of p dx, is simply substitution to this antiderivative from 1 to b. And then we must take limit as b goes to the infinity. That limit, if it is finite, then it is the value of this improper integral. Now the substitution gives that the improper integral from 1 to the infinity dx divided by x to the power p is the limit as b goes to the infinity of b to the power 1 minus p divided by 1 minus p minus 1 to the power 1 minus p, that is just 1, divided by 1 minus p. Here, negative of p plus 1 is more conveniently written as 1 minus p. Now, if this limit exists and is finite, then this improper integral from 1 to the infinity dx divided by x to the power p converges. And in that case, the value of this limit is also the value of this integral. Now, this limit is finite only if the power of b, that is 1 minus p, is negative. If 1 minus p is negative, then b raised to that power approaches 0 as b goes to the infinity. If 1 minus p is positive, then b to that power approaches positive infinity as b goes to the infinity. The case that 1 minus p equals 0 is already excluded since we assume that p is different from 1. So assuming that 1 minus p is negative, this limit is just 1 divided by p minus 1. So this in case 1 minus p is negative. If 1 minus p is not negative, then this integral diverges, that is, the corresponding limit is, in this case, the infinity. So we conclude that the integral from 1 to the infinity dx divided by x to the power p converges only if 1 minus p is negative, that is, p is greater than 1. The integral from 0 to 1 dx divided by x to the power p is improper if p is positive. And in such cases, this integral must be defined as a limit as a goes to 0 through positive numbers of integrals from a to 1 dx divided by x to the power p. So we assume that p is positive. We also assume that p is not 1, because that is a special case and can be dealt with directly. If p is not positive, then this integral is not improper and can be computed without any problems at all. So now we assume that p is positive and different from 1. We write the integral from a to 1 dx divided by x to the power p as the integral from a to 1 x to the power negative of p dx. Now, this x to the power negative p is easy to integrate. An antiderivative is x to the power negative p plus 1 divided by negative p plus 1, and then we substitute from a to 1 and take the limit of this expression as a goes to 0 through positive numbers. Now the substitution yields, the upper limit gives 1 divided by 1 minus p, and the lower limit yields a to the power negative p plus 1 divided by 1 minus p. And a now approaches 0 through positive numbers. Now a to the power negative p plus 1 approaches also 0 if the exponent negative p plus 1 is positive. If negative p plus 1 is negative, then a to the power negative p plus 1 approaches the infinity as a approaches 0 through positive numbers. So this has the finite limit 1 divided by 1 minus p, assuming that the power of a, that is negative p plus 1, is positive. And this means that p is less than 1. So if p is less than 1, the integral from 0 to 1 dx divided by x to the power p converges. Its value is 1 divided by 1 minus p. And if p is 1 or greater, that integral diverges. The integral from 1 to the infinity e to the ax dx has to be computed as the limit as b goes to the infinity of the integrals from 1 to b e to the ax dx. Observe first that if a equals 0, then e to the ax is e to the 0, which is 1. Integral from 1 to b of 1 dx is just b minus 1, and that has infinite limit as b goes to the infinity. Therefore, if a equals 0, this integral diverges. Now assume that a is not 0. If this is the case, then we may find an antiderivative of e to the ax easily. It is e to the ax divided by a. We substitute from 1 to b, and we let b go to the infinity. When we perform the substitution, we get e to the ab divided by a minus e to the a divided by a. And here b is the variable that approaches the infinity. If a is positive, then as b approaches the infinity, e to the ab also approaches the infinity. Therefore, if a is positive, then this expression e to the ab divided by a minus e to the a divided by a has the infinity as its limit. If a is negative, then e to the ab approaches 0 as b approaches the infinity. So if a is negative, the first term e to the ab divided by a approaches 0, and the term minus e to the a divided by a remains, and that is then also the limit. So if a is negative, then the improper integral from 1 to the infinity e to the ax dx converges, and it has a value minus e to the a divided by a. Observe that now, since a was assumed to be negative, minus e to the a divided by a is actually positive. If a is not negative, then the integral diverges. We may summarize the previous examples to the following list of basic improper integrals. First, integral from 1 to the infinity dx divided by x to the power p converges if p is greater than 1 and otherwise diverges. This integral is improper because the interval of integration is infinitely long. Integral from 0 to 1 dx divided by x to the power p converges if p is less than 1. This integral is improper because if p is positive, then the function to be integrated 1 divided by x to the power p is undefined when x is 0. The third type is integral from 1 to the infinity e to the ax dx converges if the coefficient a is negative. Fourth, integral from 1 to the infinity x to the power p dx. This is similar to the integral of the type number 1. This converges if p is less than negative 1. And number 5, integral from 0 to 1 x to the power p dx converges if p is greater than negative 1. So this again is a normal integral if p is positive. It is an improper integral if p is negative, because then x to the power p is undefined at x equals 0. These are the basic improper integrals to which we may compare other integrals to figure out whether they converge or not. Often it is not possible to compute the limit defining a given improper integral directly. It may be impossible to perform the integration. In order to find out whether such an integral converges or not, one can try to compare that integral to a known integral of which we know that it either converges or diverges. Often these known integrals are one of these basic types of improper integrals. For example, consider the improper integral from 0 to the infinity 3 divided by the product of 1 plus 2 times sine squared of 4 pi x and 1 plus x squared. This is a quite complicated function, and the integration is hopeless. The graph of this function is the red curve shown in this figure. Now, we observe that this red curve takes positive values. So the improper integral from 0 to the infinity of this positive function 3 divided by 1 plus 2 times sine squared of 4 pi x, and that sum multiplied by the sum 1 plus x squared, then this improper integral, if it is finite, if this improper integral converges, its value is the area of the domain under the red curve. And conversely, if the area of the domain under the red curve is finite, then this improper integral converges. So this is the idea of the so-called comparison theorem. And in this particular case, it turns out that this improper integral converges, and we can show that by finding a simpler function. And in this case, it is a function whose graph is the blue curve in this figure, such that the area under the graph of the blue curve is finite. If this is finite, then also the smaller area under the graph of the red curve is finite. To do that, we observe first that for all values of x, of course, sine squared of 4 pi x is positive or 0. And 2 times that is also positive or 0 for all values of x. Therefore, in the denominator, the factor 1 plus 2 times sine squared 4 pi x is always greater than or equal to 1. So if we replace that factor by the lower limit 1, we get an upper limit for the whole expression. So we observe that, first of all, this quantity to be integrated, 3 divided by 1 plus 2 times sine squared of 4 pi x, and that sum multiplied by 1 plus x squared is positive, and it is less than or equal to 3 divided by 1 plus x squared. We have equality whenever sine of 4 pi x is 0. Otherwise, we have strict inequality. The graph of the function 3 divided by 1 plus x squared is the blue curve shown in this figure. And for this function 3 divided by 1 plus x squared, we can actually compute the improper integral directly using basic methods. So we observe that the integral from 0 to the infinity 3 divided by 1 plus x squared dx is substitution to 3 times, well, it is 3 times integral from 0 to the infinity dx divided by 1 plus x squared. We take limit of that as b goes to the infinity. And this integral is substitution to 3 times arctangent of x, and substitution from 0 to b, we take limit as b goes to the infinity. And this quantity is just 3 times arctangent of b minus 3 times arctangent of 0. And we take limit as b goes to the infinity. And this limit is 3 pi over 2. Arctangent of 0 is 0. The limit of arctangent of b as b goes to the infinity is pi over 2. And we had the coefficient 3, so we get the result 3 pi over 2. And then, since we had this double inequality, 0 less than 3 divided by 1 plus 2 times sine squared of 4 pi x, and that sum multiplied by 1 plus x squared is less than or equal to 3 divided by 1 plus x squared, we conclude that this integral from 0 to the infinity, 3 divided by 1 plus 2 times sine squared 4 pi x, and that multiplied by 1 plus x squared must be finite, so this improper integral converges. The comparison theorem for improper integrals has two parts. The first part gives a condition under which a given improper integral converges, and the second part gives another condition under which another given improper integral diverges. So now we consider the interval of integration from a to b, where a can be also a negative infinity and b can be positive infinity. We assume that between a and b, f of x is always greater or equal to 0 and at most g of x. So we assume that both functions f and g take non-negative values, and that f at x is at most g at x for all x. If both f and g take non-negative values, then the improper integrals from a to b g of x dx and improper integral from a to b f of x dx, they are areas of domains under the graph of g and under the graph of f correspondingly. If these areas are finite, then these improper integrals converge. And now, if the function g takes values that are greater or equal to the values of the function f, then it means that the domain under the graph of g contains the domain under the graph of f. And therefore, if the improper integral from a to b g of x dx converges, then it means that this domain under the graph of f must have a finite area. And then, since the domain under the graph of f is included into this domain under the graph of g, which has finite area, then also the domain under the graph of f must have a finite area. And therefore, if the improper integral from a to b g of x dx converges, then also the improper integral from a to b f of x dx converges, and we have this inequality. 0 is at most integral from a to b f of x dx, and this is at most integral from a to b g of x dx. So this part of the comparison theorem follows by by the fact that if a domain is contained in another domain which has a finite area, then this first domain must also have a finite area. Now, part B is the following. If the improper integral from a to b f of x dx diverges, then also the improper integral from a to b g of x dx diverges. And if this improper integral from a to b f of x dx diverges, this means that the domain under the graph of f has an infinite area. And since that domain is included into the domain under the graph of G, then also the domain under the graph of G must have an infinite area. And this means that the improper integral from a to b g of x dx diverges. So these are the two statements of the comparison theorem. As an example of the use of the comparison theorem, let us consider the question, does the integral from 0 to 1 dx divided by sine of x converge? This is most conveniently solved by observing that when x is between 0 and 1, then sine of x is between 0 and x. If x equals 0, then sine of x is 0 and also x is 0. Then we have equality here, but if x is between 0 and 1, sine of x is positive and less than x. This follows from the definition of the function sine and can be also shown to be true by considering the function x minus sine of x. This function is increasing and it takes the value 0 when x equals 0. Therefore, this function x minus sine of x is positive when x is positive. Now, since 0 is less than sine of x, less than x, when x is between 0 and 1, then we conclude that 1 divided by x is between 0 and 1 divided by sine of x. This is valid when x is greater than 0 and at most 1. And now this suffices because we know that this improper integral from 0 to 1 dx divided by x, this is one of the basic types of improper integrals. And we do know that that diverges. And we can conclude by the comparison theorem that also the integral from 0 to 1 dx divided by sine of x diverges. To summarize this discussion, we list the basic improper integrals of which we know when they converge and when they diverge. The first one is integral from 1 to the infinity dx divided by x to the power p. This converges if p is greater than 1. Related to this is the integral from 1 to the infinity x to the power p dx, and that converges if p is less than negative 1. This is then integral of type 4. Integral of type 2 is integral from 0 to 1 dx divided by x to the power p. It converges if p is less than 1. The integral from 1 to the infinity e to the ax dx converges if a is negative. And this number 4, integral from 1 to the infinity x to the power p dx converges if p is less than negative 1. And integral from 0 to 1 x to the power p dx converges if p is greater than negative 1. And for all other values of the parameters in the above integrals, the integrals diverge. And then we may use the comparison theorem and compare complicated integrals to one of these basic types of improper integrals, and then we can show that these complicated integrals either converge or they diverge. Knowing that an improper integral converges is important, because if it converges, then we know that it has a finite value, and we may then try to estimate the finite value numerically by various numerical methods. But if the integral diverges, then of course it does not have a finite value, and numerical methods do not make any sense.